the length of brass bars are same, areas of brass bars are also same, but steel bar length is different, area is also different. That means whatever load is carried by this brass bar is the same as the load carried by this brass bar. So you can take these two as PB, and PS is the load carried by the steel bar. So your total P will be now PS plus PB plus PB. So that is, see, I have written here, P is equal to PS plus 2 times PB. There is your equilibrium condition now because he has given two brass bars. So we have to take 2 times PB. Yes. Now the question is find out this P. That is one thing. Then find also the actual stresses in the bars and the forces in them. That means actual stress in bar, yes, that is steel bar, that is sigma S we have to find out. Then sigma B also we have to find out. And also the forces in them. Forces in them means PS and PB also we have to find out. So that is the problem. So very important here is there is one condition that stress should not exceed 120 Newton per mm square in steel and stress should not exceed 60 Newton per mm square in brass. So that is important thing here. There is a difference between the earlier problem and this problem. So unknowns are here in this problem. Total load P is unknown, stress in steel is unknown, stress in brass is unknown, load carried by steel rod is unknown, load in brass bar is unknown. So these are the unknowns. So understand the problem. It's a problem of a composite bar only. Only thing is there are three bars here. One is steel bar, two are brass bars. Steel bar area 1500 mm square, length is 170 mm. Brass bars area 1000 millimeter square and length is 100 mm. Total load is P, which is unknown. And the stress in steel should not exceed 120 Newton per mm square. Stress in brass should not exceed 60 Newton per mm square. These are the conditions. So as usual, we have to apply the same equilibrium, that is same conditions. First one is the equilibrium condition. In this case, since there are two brass bars, P will be equal to PS plus 2 times PB. So there are two brass bars. PB is the force carried by that single brass bar. So two brass bars are there. So 2 times PB. So this PS can be written as sigma S into AS. So force carried is equal to stress into area. Sigma into AS plus 2 times sigma B into AB. So stress in brass bar into area of brass bar. So now he has given the values of AS and AB. You know? So AS is 1500 mm square. AB is 1500 AS value mm square. AB is 1000 mm square. So if you substitute that, you will get this. So here sigma S and sigma B are unknowns. Second condition is that strain compatibility condition. In that case, we are using the same deformation in steel bar is equal to deformation in the brass bar. Delta LS is equal to delta LB. So if you substitute the formula for delta L, PL by AE, so you will be getting PS LS by AS ES is equal to PB LB by AB EB. Now whatever values you know, all those values you substitute. Length of steel bar is 170 mm, length of brass bar is 100 mm, PS and PB are unknowns, AS you know, so it is, otherwise you can do one thing, this PS by AS, you can write it as sigma S, then you need not substitute for AS, PB by AB can be written as sigma B. So if you substitute that, then if you simplify, you will get sigma S is equal to 1.17 sigma B. So this is the relation you are going to get between the stress values in steel and brass. So this is one equation, this is another equation. So there are two unknowns and two equations. These two equations, he has given one condition here that it should not be greater than 120. So we had to test, we had to check whether that condition is satisfied or not. Now let us take first case. What I will do is, I will take sigma S as 120. If you put sigma S as 120, what happens to sigma B? Maximum value of stress in steel is restricted to 120. Let us take that steel rod has taken the maximum value of stress, which is 120. Then using this equation, get the value of sigma b. So sigma b is sigma s divided by 1.17, 120 divided by 1.17, which is 102.56. But what he has given, sigma b should not be greater than 60, or it should be less than or equal to 60. So the maximum value of sigma b is 60 Newton per mm square. But here you are getting sigma b as 102, which is not permissible. So that is, it is greater than 60, therefore it is unsafe. Very, very important. So the stress in brass bar is exceeding 60, greater than 60, which is not safe. That bar will break. That is the main. Now, second case is, he has given that the maximum value of stress in brass bar is 60. Let us use that one here. So let sigma b is 60. Find out the corresponding value of sigma s. Sigma s we have found out it is 1.17 times sigma b. So 1.17 times 60, 70.2. So we know that stress in steel should not exceed 120. This is less than 120. Since it is coming less than 120, it is safe. So that means we have to use this condition now. So considering the safest condition, considering second case, so we have got sigma, we have got sigma s as 70.2, brass as 60. Okay, so this condition only we are using, but we are testing this condition for two cases by taking the highest value in steel and highest value in brass. That is the important criteria here. So in the second case, we have got the safest condition. Therefore, these are the values, actual values. So these are the actual stresses in this thing. Now, what happens here is, second part he has asked what is the load. So now we have calculated sigma s and sigma b is over. Next p we have to find out, then ps and pb we have to find out. So to find p, what we have to do? So we are using this condition. First condition, we have got this expression, p is equal to 1500 sigma s plus 2000 sigma b. In that you substitute the value of sigma s and sigma b, you will get the value of p. So p is equal to 1500 into 70.2. 70.2 is sigma s plus 2000 into 60. Whatever you get, this will be in newtons. Please note that this is Newton per mm square. This is mm square. This is Newton per mm square. This is mm square. This is Newton per mm square. So if you mm square is cancelled out, you'll be getting in newtons. That if you convert to kilonewton, you'll get this. Divide by 1000 if you do. So this is the value of the total force acting on the system, 225.3 kilonewton. Actually, it is 225.3 into 10 power 3 newton. So you'll be getting 225.3 kilonewton. That is the answer. Now, he has asked the force in steel as well as force in brass. So PS and PB has asked. We know that PS is given by area into stress. So PS is equal to sigma s into AS. So if you substitute that, sigma s is 70.2, AS is this, you will get this much. And force in brass bar is PB, which is sigma B into AB. So sigma B is 60, AB is 1000, so 60 kilonewton. So force in the each brass bar is 60 kilonewton. Force in steel bar is 105.3. If you want the check is like this, we know that P is equal to PS plus 2 times PB. So PS is 105.3, PB is 60. If you substitute, you will get 225.3. That is the value of P. So this is how we have to do. In this problem, the only difference is he has given the maximum value of stress in steel and brass bars. Sigma s and sigma b values, he has given the maximum values. So we have to consider both of them separately. Assuming steel has reached its maximum stress value, by taking sigma s is equal to 120 Newton per mm square, calculate the corresponding sigma b value. So if you do that, sigma b is getting more than 60, so therefore it becomes unsafe because it should be less than 60. In the other case, if you assume that brass bar has reached its maximum stress value first, so sigma b is 60, corresponding sigma s value is 70.2, which is less than 120. So 120 is the maximum stress in steel, so it is safe. So we have to take the safer condition, and we have to move further by using the same equations. So that is one important problem. Now the next problem, there are two vertical rods, one of steel and the other of copper. Cu means copper. So this is copper, this is steel. Both are having the 20 diameter. So length is also same. So both are having 4 centimeter length. Rigidly fixed at 50 centimeter apart. So the distance between these two is 50 centimeters or 500 So if you convert everything to millimeters, it is 500 Distance between center to center of this is 500 on the top of a crossbar. This is the crossbar. This is called as the crossbar. So it is hanging like this. The diameter and length of each rod are 2 centimeter and 4 centimeter respectively. So 2 centimeter diameter, both rods, that is 20 diameter. Length is 4 centimeter, that is 40 length of both the bars. The crossbar carries a load of 5 kilonewton, such that it remains horizontal even after loading. So what happens? This bar carries a point load of 5 kilonewton, but we don't know the distance. At what distance that 5 kilonewton load is applied? So we have to take that distance as x. Take that distance as x. So that distance we have to find out here. So some load, 5 kilonewton load is applied here at a distance x from this end. Okay, that means that distance from the load distance from this end will be 500 minus x from the copper. So the thing is such that it remains horizontal. That means it remains horizontal means elongation of this rod and elongation of this rod should be same. That is the meaning. Strain in this and strain in this should be same. Then only it will be horizontal after applying that kilonewton force. After loading, find sigma, that is stress in each bar, and the position of load on crossbar. That is the x value we have to find out, stresses we have to find out, as well as we can find out the forces also, force in this and force in this. So stresses in these two bars, steel and copper bars, due to the weight due to the force 5 kilonewton applied on the crossbar. So we don't know the position where this 5 kilonewton is applied. We are going to assume that position as x from the steel bar. So it will be 500 minus x from the copper bar. So this is the diagram. So Young's modulus values of both steel and copper are given. So this is actually not brass. This is copper. So Cu. You can make it as ECU. Yes. Now as per the equilibrium condition, first condition is P is equal to PS plus PC. So this whatever P is there. P is here this. 5 kilonewton is the load. Total force acting on this. So this 5 into 10 cube we have to write is equal to PS plus PC means sigma S into AS plus sigma C into AC. Stress multiplied by area gives the force. So sigma S into area of steel is pi into 20 square by 4. So diameter of the bar is 20 plus sigma C into this is also same. So 20 diameter, same diameter he has given. So this also area remains same. If you simplify this, you will get sigma S plus sigma C is equal to 15.915. This is one equation. This is one equation. Second equation is strain compatibility equation, which says that delta LS is equal to delta LC. So we know that delta L is PL by AE. So this is the equation. PSLS by ASES for steel is equal to PCLC by ACEC for copper. So here LS is equal to LC. You know that from the diagram you can see that length of steel bar and length of copper bar they are same. So that can be cancelled out. So PS by AS is nothing but sigma S. Okay. So LS and LC cancelled out. Divided by ES is 2 into 10 power 5 MPa. Heat has been given. Young's modulus of steel. Young's modulus of copper is given 1 into 10 power 5. If you simplify this, you will get sigma S is equal to 2 times sigma C. So 2 times sigma C. So this is the relation. Now using these two, you can find out the values of sigma S and sigma C, stress values. So if you substitute in this for sigma S as 2 times sigma C, it becomes 2 sigma C plus sigma C, that is 3 sigma C. So 3 sigma C will be equal to 15.915 or sigma C will be 5.3 Newton per mm square. Substitute that value of sigma C here, you will get sigma S. Sigma S as 10.6. So these are the stresses in the two bars, sigma S and sigma C. Now if you want the forces, so forces are PS is equal to sigma S into AS. We know that force is given by stress into area. So if you multiply that, so sigma S is 10.6 into AS. AS is pi into 20 square by 4. This is your area of steel. If you substitute that, you will get 3330 Newton. It will be in newtons. Okay. Convert that into kilonewton. 3.33 kilonewton. Similarly, force in copper bar will be sigma C into AC. Stress into area. So stress in copper is 5.3 multiplied by area of copper. Area of copper rod is also same, pi into 20 square by 4. So if you substitute that, you will get in newtons. Divide by 1000, you will get in kilonewton. So PS and PC, if you add these two, you should get 5. So see, just add these two, you are getting 5. So that means P is equal to PS plus PC. P is 5 kilonewton, PS is 3.33, PC is 1.665. So actually this will be, I think, 3.335 if you take the exact value. Now that is, they are the forces in the two bars, copper and steel bars. Now position of that load we have to find out. So to find the position of the load, what we have to do is, since this is giving this is not deflecting, so you have to take the moment about any one of the points. Okay, so I will take the moment about this point A and equate it to 0. So what happens if you take the now this 3.33 kilonewton, the 3.33 kilonewton force will be acting like this, because this 5 kilonewton is acting downwards. Resistance, the force developed in the rod will be acting upwards. Please note, it's very, very important. So this is 5 kilonewton is the force acting downwards. Force in steel bar will be acting upwards. Force in brass bar also, the copper bar also will be acting upwards. This value is 3.335. This value is 1.665 in copper. X is the distance between that steel bar and the load. So now to find this X, what we have to do is, we have to take the moment about this point A, some of the moments about the point A, and equate it to 0. If you are taking moment about this point A, assuming clockwise moment positive, so 5 into X. 5 into X is the moment due to this 5 kilonewton. Clockwise is positive. This 5 kilonewton is acting giving a clockwise moment. 1.665 is giving an anti-clockwise moment like this about this point A. So now the thing is, so 5 into X minus 1.665 into 500, distance is 500, is equal to 0. That is, or in other words, you can do like this also. If you take the total clockwise moment and anti-clockwise moment, they should be equal. That is also okay. If you do like that, then if you take this point C as reference, this is giving clockwise momentum. 3.335 into X should be equal to 1.665 into 500 minus X. Like that also you can do. So you will get the same answer. The X distance is 166.5 mm. That's what you are getting. So this is how we have to do this problem. So all these are important. So in this problem, the difference is, we are applying a load or force at some other point. Here. See the difference between these problems. Here, load is applied on all the three. Okay, it is shared by all the three bars here. Whereas here, load is acting not on the bars. It is acting somewhere else. In that case, that moment will come into picture. When load is not acting along the bars, then that moment we have to take. That is very important. Now the next problem also. Yeah, here also the load is not acting on the bar, it is acting somewhere else. See the diagram here. If you see the diagram clearly, there is a horizontal bar here. AD is the horizontal bar. It is hinged at the end A. Hinge means the moment will be 0 at the hinge. If you find the moments due to all the forces, it will become 0. Some of the moments will be 0 at the hinge end. Now there is a brass rod here at B. Distance is 1 meter from here. Then there is a steel rod here at C. Distance is 2 meters. So from here to here it is 1. From here to here it is 1 meter. Then the load is acting somewhere here at D. 10 kilonewton load is acting. That is 0.75 meter from here. So you see the arrangement here. So here the rod is above this bar. Here the rod is below the bar. Load is acting downwards. Brass bar has a length of 1 meter. Area 1000 mm square. Area of brass bar is 1000 mm square. Length is 1 meter. That is LB is 1 meter. AB is 1000 mm square. Steel bar having length 2 meters. Area 600 mm square. So that means LS is 2 meter. Length of steel bar is 2 meter. Area of steel bar AS is 600 mm square. Load is acting here. So from this end to this end it is 2.75 meter. You should be very careful in such type of problem. Here also has asked a rigid bar ABCD is hinged at A and is connected to brass and steel rods as shown in the figure. Find the stresses developed in the rods if the areas of brass and steel rods are 1000 mm square and 600 mm square respectively. If a load of 10 kilonewton acts at the end D. So that's what the figure is. The figure says take ES, Young's modulus of steel as 2 into 10 power 5 MPa or Newton per mm square, and EB, Young's modulus of brass as 1 into 10 power 5 MPa or Newton per mm square. So here also we have to find the stresses in each rod, as well as you can find the forces also, force carried in each rod. So we have to use the same condition, strain compatibility condition and equilibrium condition. But what happens here, the load is not acting on the bar. So it is not a direct load. So it is acting somewhere else. Very important. So somewhere else it is acting. Then in that case, you have to, in this problem you see, due to this load, this bar tries to come down. See here, this is the deflected shape. We call this as deflected shape. Due to this load, so this is hinged here. Here there is no deflection, but this bar tends to deflect like this. This is how it tries to deflect due to this thing. Once this deflection takes place, what happens here? You can observe. Initially, it is like this. Once it gets deflected, what happens here? This brass rod tries to elongate. See here the arrangement, because the brass rod is one side, steel rod is another side. They are not on the same side. Brass rod, the length is increased here, whereas for steel rod the length will decrease. That means this is subjected to a compressive stress. This is subjected to a tensile stress. Understand this problem clearly. So due to this load, the bar bends like this. This horizontal bar bends like this. This will elongate. This bar will contract. If both of them are on the same side, then suppose let us say both the bars are on the upper side of this bar, then both will elongate. If both the bars are on downside of this straight bar, then both will contract. But here, brass bar is elongated, the steel bar is contracted. Now let me take the elongation as delta LB for the brass, that is tension. Delta LS I will take compression, that is contraction. I will take delta LS as the contraction in the steel bar. So very important. Now you can get a relationship between this delta LS and delta LB in this case. So if you observe this similar triangle, see I have written, if you take a triangle like this, similar triangle, there will be two triangles. This is delta LB, this is delta LS, 1 meter, 1 meter. This is from here to here 1 meter, from here to here 1 meter. If you observe the similar triangle, I hope you know the property of similar triangle. Respective sides are proportional to each other. So delta LB divided by delta LS will be equal to 1 divided by 2. So that means your delta LS is 2 times delta LB. So it will be exactly 2 times. So it is not, both are not equal here. Both of them will be equal only if it is the force is acting on the bar. But here force is not acting on the bar. It is acting somewhere else. And this relationship is obtained by taking the deflected shape like this. So in this case, the strain compatibility condition is delta LS is 2 times delta LB. This is a very important step. So once you get this, so delta LS is nothing but PL by AE. So PL by P by A is nothing but sigma. So sigma S LS by ES is equal to 2 times. This 2 times is important here. So sigma B LB by EB. Okay. Now substitute whatever values you know. So LS is 2000 here. So length of steel rod is 2000 mm. It is in meters. Convert 2 meters. It will convert into millimeter. So sigma S into 2000 divided by ES value is 2 into 10 power 5 for steel is 2 times sigma B into LB is 1000 meter. 1000 mm. Brass length is 1 meter. 1000 mm divided by EB value 1 into 10 power 5. Just substitute that, get the relation. If you simplify that, you will get sigma s is equal to 2 times sigma b. Sigma s is equal to 2 times sigma b. This is one important relation between the stress values in steel and brass. Now apply the equilibrium condition. Now here, since the load is not acting on the bar, it is acting somewhere else. We have to take the moments. So that is in the last problem also we did like that. The load is not acting on the bar. It is acting somewhere else with some distance. Then moment will come into picture. He has given that there is a hinge point here. Now the equilibrium condition is sigma ma is equal to 0. This is the equilibrium condition. So you have studied the equilibrium conditions in your first semester, that is mechanics subject for finding support reactions and all. You have for concurrent force system only two equilibrium conditions. Sigma fx is equal to 0, sigma fy is equal to 0. They are the force equilibrium conditions in both the directions x and y. If you take a non-concurrent force system, you will be having three equilibrium conditions in two dimension. That is sigma fx0, sigma fy0, sigma m0. Moment equation also comes into picture. Now, if you find the moments due to all the forces here, see how I have written. So one diagram I have written here, A, B, C, D. So PB and PS I have taken like this. Here you please note that PB is the force in brass, PS is the force in steel. Okay, and they are acting at distances 1 meter and 1 meter. End A. So this PB multiplied by 1, PB into 1 plus PS into 2, PS into 2 should be equal to 10 into 2.75. So assuming that this is anti-clockwise, this is anti-clockwise, this is clockwise. So moment due to clockwise moment should be equal to anti-clockwise moment. So these two are giving anti-clockwise moments. This is giving clockwise moment about A. So PB into 1 plus PS into 2 should be equal to 10 into 2.75. So if you simplify this, PB plus 2PS is equal to this value you will get. Or you can substitute now for PB as sigma B into AB, PS as sigma S into AS. So force is equal to stress into area. You will get this. Now substitute for AB and AS. So area of brass and area of steel you will be knowing. It is given here. So area of brass is 1000 mm square. Area of steel is 600 mm square. If you substitute for AB and AS and if you simplify, you will get another equation like this. So now you have got two equations. One is this strain compatibility equation is sigma s is equal to 2 times sigma b. Equilibrium condition is this. This is equilibrium condition. Now you have to solve these two. So what you can do is in this equation you can substitute for sigma s as 2 times sigma b. So this can be written as 2 times sigma b. So if you do that, so see I have written here. So sigma b only will be the unknown. If you simplify that, you will get sigma b as 8.088. So it is tensile stress. Please note that this is tensile stress. Sigma B is tensile because that bar is extended. Bar is extended. Brass bar is extended, whereas steel bar is contracted. It is compressive stress. That is the difference. Numerical value you can find out and you can write in brackets. Why it is tensile stress? Because if you see the diagram here, due to this load, this bar bends like this. So brass bar is elongated, length will increase, whereas steel bar contracts, length will decrease. So when length decreases, it is compressive stress. When length increases, it is tensile stress. So that is why. So these values, tensile stress and compressive stress. Now, if you want the forces in the two bars, steel and brass bars, PS is sigma s into AS. So sigma s is this value, 16.176 into AS is 600 mm square. If you multiply, you will get the force in Newton divided by 1000, you will get in kilonewton. So PB is sigma B into AB, you will get this value. So here, one thing you can write here is this PS is once again compressive force, PB is tensile force. PB is tensile force. So now if you want to check, so PS you have got 9.7, PB you have got 8.08, So now, if you want to check, you can substitute here in the expression, and you can check it. Anyway, that is not required. So you can write force in steel bar as tensile force. You can write in brackets tensile force. Sorry, force in steel bar is compressive force. This is 9.7 is compressive force, whereas 8.08 kilonewton is tensile force. So these are very important types of problems in compound bars. You can refer textbook. Some more problems have been done in the exercise or in the worked examples. You can see a lot of problems in the textbooks. I want you to study that also. So I think I have covered many lot of problems on compound bars also. So till now, what we have discussed, I will just explain in nutshell. So in the beginning class, we studied about the types of stresses: linear stress, lateral stress, and linear strain, lateral strain. Also we studied. Then Hooke's law. Then after that, we found out the stresses in compound that stepped bars and uniform bar, and as well as tapering bars. In tapering bar, you have got two types: circular and rectangular. How to find the deformation derivations we have done, and numerical examples related to all these three types: stepped, uniform, tapering. All the types we did. Then we did some problems of restraint conditions on both sides, stepped bars with restraint condition, where you are asked to find the reactions and all, and stresses as well. No, those things, those types of problems we covered. And after that, I told you about that tension test, how that mild steel specimen is subject to tension test, and how to get the percentage elongation, percentage reduction in area, and Young's modulus from the data of load and deflection or deformation that we discussed, and some problems we did on that. Then I came to compound bars. So what is a compound bar, and how to find the stresses in compound bar when the force is directly acting on the bar? What are the conditions, equilibrium condition as well as the strain compatibility condition? Then I discussed about the compound bars only, but the load is not acting exactly on the bar; it is acting somewhere else. So then how to, we have to consider the moment equation also for equilibrium condition, and how to solve the problems. So these are the types I have discussed till now. Now in the next class, I will be going for principle of superposition, then about that Poisson's ratio, this is another elastic constant, then bulk modulus of elasticity, then shear stress, generalized Hooke's law. A lot of things are there to discuss. So I will be taking that this in the next class. So we have to work the same problem. What I advise you is work out the same problems in the notes. Whatever I have done here, same problems you write down, sketches, and try to use the formulae and substitution everything, because all the steps are not there in this. So you have to work. So unless you work, and if you have soft copy of any textbook, you just you can download. So if you give the title, you can download the textbook also in our strength of materials. So only thing is you should be careful about the notations. So as I already told, I am using sigma for stress, epsilon for strain, P for the force, A for the area, E for Young's modulus. So like that. So some books they may use little bit different notation. You should be careful about that. That's all. Other thing, concept remains same. Only those notations may be different. That you should be a little bit careful. So try to practice more number of problems. So in the next class, that is on Monday, I will be taking the next concept: principle of superposition, generalized Hooke's law, shear stress, all those things. Shear stress I have not yet come. So still I am doing only tensor and compressive stress. So shear stress also we have to learn. This first module is a very big module. So a lot of information is available in the first module, but it is very important. You cannot skip this first module, so it will be difficult to understand you the remaining topics. So I advise you to go through whatever notes I have sent by PDF. Some more I will be sending, and in addition to that, refer any one or two textbooks. So Strength of Materials by Basavarajaya and Mahadevappa. It is a good book. Basavaraj and Mahadev is a good book. You can just download it if it is available. Otherwise, you can that R.K. Bansal is also okay. Strength of Materials by R.K. Bansal. That book also, I think it is available. It is available. Soft copy is available. Go to the go to net and you can download it. You always you should have one or two textbooks soft copy with you or hard copy, just to have if you have any doubts, you can refer it immediately because in the notes everything may not be available. So since I have prepared the notes, I am going to explain using that. So if you have any doubts and all, immediately you can refer the textbook. It is also always I advise you to refer textbooks also. Worked examples, same problems you try to work it out, and some problems in the exercise also. Answers will be there. You can cross check the answers. And another thing is you should be very careful about using the units. Units are also very important. Newton per mm square. I told you that all the forces you convert into Newton, areas, length, everything into millimeters because stress value will be Newton per mm square. Young's modulus value will be Newton per mm square or MPa. So better you convert all the force values and the stress value, force values in newtons and length units in millimeters and area in millimeters square. So this is what I wanted to explain you. If you have any doubt, you can ask me. You have any doubt? Only 10 students are there. Okay, let me take the attendance. 002.
Yes, sir.
005.
Present, sir.
006.
Present, sir.
007.
Present, sir.
010.
Present, sir.
011. 011.
Sir, present, sir. Preeti.
013.
Present, sir.
018.
Present, sir.
019.
Present, sir.
I think that's all. Nobody else has joined.
Sir, 017.
017 I called. Yeah, I called. This is seen here on the screen. Only I think 10, 3, 4, 5, 6, 7, 8, 9, 10.
Sir, 018.
016, 19.
18.
18 I have taken. 18, 19 I have taken. Okay. Only 10 students are there. 0. Okay. So try to work it out. Whatever problems I have explained. Once you, I don't know when you will be coming to college. When you start coming to college, I will just brush up. Only revise within 1 or 2 classes. I am going to revise and then I will start the new topic. So till then, you have to work at home only. Okay. Okay. Best of luck. So I think I will be continuing on Monday. If you have any doubts, you keep your doubts. If anything has to be asked, you can ask me on Monday. You just see all the problems, whatever have been worked. Have a notes. Same thing you write. Whatever I have explained in this PDF, same thing you try to note down and work it out. Okay, thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Okay, thank you.